Friends, welcome to the 21st lecture in module 1. We have been discussing about the computer methods of structural analysis applied to offshore structures. We have been taking examples of beam element, truss element with planar and non-planar members involved in a structural system on a 2-dimensional analysis. In the last lecture, we introduced the 3-dimensional analysis and the member stiffness matrix of size 12 by 12. We derived the stiffness matrix for the member which is on a space frame. Now, in this lecture we are going to discuss about how do we obtain or derive the transformation matrix. Now, the first question comes, why transformation matrix is important? Very simple reason, we all know that in a space frame, members can be oriented in any fashion. To be very specific, the local axis of the member may not coincide with the reference axis system. In such situation, whatever stiffness matrix we derived in the last lecture, they are considered to be local and they need to be transformed. Which is with respect to the reference axis system. Secondly, whatever load which is applied on the local need to be also transformed to get J bar with reference to the x, y, z system. Most importantly, the member forces, end moments and reactions need to be computed with respect to the reference axis system, but need to be also transformed to the local axis system of each member. The question is why this is required? This is required because to design the member. So, now the question is, in a space frame, members oriented in different formats and alignments, how do we transform them to match the alignment with that of the reference axis system? So, that is what we are going to discuss today in this lecture, which we call as a transformation matrix. One can see here V0 is a vector which is arbitrarily oriented. Okay. This V0 vector is oriented along the axis y0. Now, I want to transform this to the reference axis system. For example, we have considered the reference axis here as y1, y2 and y3 axis, which also has an orientation with reference to x, y, z plane, but let us say I want to transform this to y 1 y 2 axis. You can see here y 1 y 2 and y 3 axis are different from that of the y 0 axis along which the vector or the member is oriented. Now, let us define the angles. V 0 is a vector which is oriented with respect to some set of orthogonal axes y 1, y 2, y 3. Now, vector V 0 has its components. Along y 1, y 2 and y 3 axis. To know its component, we should like to know the inclination of this vector or position of this vector with reference to these 3 axes. Let us look at this symbol. This is gamma 0 1. So, for example, gamma 0 1 is the angle between the y 0 and y 1 axis. So, the first letter stands for y 0 and the second subscript stands for y 1. With that algorithm, please look at this angle y 0 2, this is an inclination with respect to y 0 and y 2. Similarly, y 0 and y 3 will give gamma 0 3. So, gamma 0 1, gamma 0 2, gamma 0 3 are now the angles between the y 0 axis and y 1, y 2 or y 3 respectively. Now, the corresponding components of them along y 1, y 2, y 3 are marked in blue color and they are V 1, V 2 and V 3. So, this should be V 3, this is V 3 and this is V 2 okay, along V 1, V 2 and V 3. So, one can easily find the following relationship valid: V 1, V 2 and V 3 will be V 0 cos gamma 0 1, V 0 cos gamma 0 2 and V 0 cos gamma 0 3. I call this equation number as 1, whereas gamma 0 1, gamma 0 2 and gamma 0 3 are defined as angles between the vector V 0 or the axis y 0 to which vector is placed. And the coordinate axis y 1, y 2 and y 3 respectively. Now, the above equation 1, the terms cos gamma 1, cos gamma 0 2, cos gamma 0 3 are called direction cosines. Okay. Now, we have resolved the vector V 0 along y 1, y 2, y 3 which are some set of coordinate axes. Let us now resolve this or transform this to a standard reference axis system which is x y z. So, let us now draw a figure where the standard reference axis, let x 1, x 2 and x 3 be the reference axis, as shown in the figure. So, let us name the figures. This will be figure 1, okay, which has component of vector v 0 along coordinate axis. Okay. Let this be figure 2, where we are looking at components of v 0 along reference axis. Okay. Let x 1, x 2, x 1, x 2 and x 3 be the reference axis. Okay. Obviously, this vector has a mistake, this was v 3 and this was v 2. I borrowed this figure from the previous. Okay. Now, let us define the angles. Now, let us define the angles of x 1, x 2 and x 3 and the vector v 0 or vector v 1, v 2 and v 3, because vectors v 1, v 2, v 3 are already resolved along y 1, y 2, y 3, is it not? We already have this. You can see here v 1 we have, okay, v 1 we have, v 2 we have along y 2 and v 3 we have along y 3. Okay. So, now I am interested in knowing what is the angle between these vectors and the reference axis system x 1, x 2, x 3. So, let us mark those angles. Let us say gamma 1 1, okay, is the angle between the v 1 axis and x 1 axis. So, the first subscript stands for v 1 axis, the second subscript stands for the x 1 axis. So, one can see here gamma 1 1. Similarly, the angle between v 1 and x 2, okay, v 1 and x 2 should be gamma 1 2. Similarly, the angle between v 1 and x 3, v 1 and x 3, that is this angle, okay, will be gamma 1 3. By that logic, I can now find or define angles between the vector v 2 with that of x 1, x 2 and x 3, like for example, v 2 vector is here, okay, x 1 is here, the angle between v 2 and x 1, okay, the angle between v 2 and x 1 is here. So, the first subscript in gamma 2 1, this stands for vector v 2 and this stands for axis x 1 and so on. So, this figure explains or defines all angles between the respective vectors v 1, v 2 and v 3, which were resolved along some coordinate axis system y 1, y 2, y 3, when a position vector v 0 is placed in space. Now, I am transforming that vector or those vectors v 1, v 2 and v 3, which were initially transformed through direction cosines along some reference axis y 1, y 2, y 3, are now being transformed to a standard set of reference axis x 1, x 2, x 3. Okay. So, we would like to do this. So, now we can still write a statement that V1 vector makes an angle gamma 1 1, gamma 1 2 and gamma 1 3, okay, with reference to x 1 x 2 x 3. Similarly, V2 vector makes an angle gamma 2 1, gamma 2 2, gamma 2 3 with reference to x 1 x 2 x 3. with reference to x 1 x 2 x 3. Similarly, V3 makes an angle gamma 3 1, gamma 3 2, gamma 3 3 with reference to x 1 x 2 x 3. Is that clear? So, this figure is clear. Okay. Now, let us write this connecting equation or the matrix which connects the transformed components of these vectors. Okay. So, what is the transformed component of this vector along x 1 x 2 x 3? That is very clear here. The transformed components are V 1 bar, V 2 bar and V 3 bar. So, now I want to connect V 1 bar, V 2 bar and V 3 bar with that of V 1, V 2, V 3, because V 1, V 2, V 3 we already know. You can see from this previous equation V 1, V 2 and V 3 are known, provided the direction cosines are measurable and the vector is known to us. Okay. So, now having known V 1, V 2, V 3, we are interested in finding out the components of those vectors resolved or transformed along the standard reference axis system x 1 x 2 x 3, which I call as V 1 bar, V 2 bar and V 3 bar. So, now we can write the governing equation which connects these two as below. So, the set of equations connecting components along x 1, x 2, x 3 system for the known components of the vector V 0 along y 1, y 2, y 3 are given below. So, I should say V 1 bar, V 2 bar, V 3 bar, or simply V 1 cos gamma 1 1 plus V 2 cos gamma 2 1 plus V 3 cos gamma 3 1, because these angles are defined with respect to x 1 axis where V 1 is the component. Similarly, with reference to x 2 axis I can still write V 1 cos gamma 1 2 plus V 2 cos gamma 2 2 plus V 3 cos gamma 3 2, because these are all with reference to axis 2, that is x 2. Similarly, with reference to axis x 3 1 3 2 3 and 3 3. I call this as equation set 2. Now, let us replace this cos term by a letter c. So, let c I j is actually equal to cos gamma I j, where I represents the y 1, y 2, y 3 axis system and j represents x 1, x 2, x 3 axis system. Okay. By that logic, I can convert equation 2 in much a simpler form as given here. So, I can now write V 1 bar, V 2 bar and V 3 bar in a matrix form as C 1 1, C 2 1, C 3 1, C 1 2, C 2 2, C 3 2 and C 3 1, C 3 2, C 1 3, C 2 3 and C 3 3. Okay. Connecting this to V 1, V 2 and V 3. Call equation number 3. I can now write a comprehensive equation of this as saying V bar is expressed as C of the space transpose of that of V where CS matrix refers to C 1 1, C 1 2, C 1 3, C 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. Okay. Friends, interestingly it also verifies that you can verify this individually, verifies that C space frame transpose matrix is as same as C space frame inverse. I call this as equation number 4 5. So, now we have very comprehensive equation which is equation 4. V bar, the component of the vector V 0 along reference axis system x 1 x 2 x 3 is simply given by the transformation matrix or the direction cosine matrix, C s if I know the components of this vector along any predefined coordinate axis system y 1, y 2, y 3. Please understand here one important statement. This refers to a reference axis system. This refers to some coordinate axis system. The important point to note that is both of them do not refer to the axis of the original vector V naught, is it not? That is very important. Having said this, instead of a vector let us consider as a member. So, I want to now find the member transformation matrix.